welcome to day 5 of the 12 Days of LiDAR. My name is Alex Billick, and today we're going to be talking about area-based inventories. So, you now know the lingo, you know the derivatives and the classes, and you can now open the data and start to look at it. Now let's figure out how we take this data and actually turn it into useful information. The two documents that I would point you to first that are very foundational to this concept are these two from the Canadian Forestry Service and the Canadian Wood Fiber Center, both authored by Dr. Joanne White and et al. There. The first one came out in 2013, the second in 2017, and they really provide a lot of foundational core information that's critical to understand some of these best practices. If you want to understand why the standard plot size and raster size is 20 meters and 400 square meters, these documents are what I'd refer you to. We're not going to dive into those; they're several hundred pages long, so take a look at those in your own time. But at a 30,000 foot level, area-based inventory is really summed up by these four pictures. You have some form of field information that is collected that we then try and create a correlation between the field data and the LiDAR data at that exact location. We build a model that describes that relationship between those two, and then we apply that model to the rest of the LiDAR on the entire land base. That's the basic logic going on here. How we locate those plots, how we build those models, what metrics we use to describe the LiDAR at the plot location are all variables that we can change. But fundamentally, that is what's going on here. When we talk about LiDAR metrics, you'll hear that term thrown around. I'm going to talk about it a lot more when I talk about fusion and when I talk about LiDAR, specifically the R package, which is where this comes from. It's a way of describing a point cloud. So what I'm going to do is just open up a visualizer here so we can look at this point cloud. This happens to be from campus again, and it's a 400 square meter circular plot that we can take a look at. So I can just circle it around here. This has been height normalized, so we're looking at height above ground here. And if we talk about a metric, we could be talking about something as simple as what percent of this plot has points above the mean versus below the mean. Now, why would that matter? Well, if you think about structure, if fundamentally we have more points higher in the canopy and not very much going on down below, maybe that's describing a conifer stand, like a pine stand, where there isn't a lot of undergrowth. Inversely, if there's a lot of undergrowth down here and not a lot in the canopy, maybe we've got some very tall trees skewing some things up and down. It's a different forest type. What we're doing is we're saying we've measured plot data here. We understand on the ground in traditional forestry terms what is going on the ground. And now we want to understand mathematically what the LiDAR data looks like and try to build as many variables as we can in some cases. There's a standard suite, which I showed you previously there, and we'll go back to. But there's many different ones that you could create to try to describe your forest condition. Fundamentally, though, it's just a way of breaking this point cloud up into some kind of statistical descriptor, whether it's percentiles. You'll often hear the 95th percentile is a depiction for stand height in that case. There's a lot of these different standard metrics that we utilize, but you might develop your own. We're not going to get into the details of the weeds about why you would choose one or the other. Just you need to understand that that is what this is coming from. All of these metrics that you see are some description. So what we're looking at here is the maximum height value that was seen in the LiDAR data at each of these points. What the mean value was, standard deviation, skew, kurtosis, entropy, the percentage of points above the mean. And then we get into percentiles here, and there's many more standard metrics than this. But you see how we can start to just describe structure. We're creating variables to then be able to create some mathematical models. One fact that is very critical to understand when we talk about area-based inventory and especially the field work is the accuracy of your plot location. In this particular example, the X represents where our field plot was collected, where our plot center was in the field, all the data we collected. The circular area represents the GIS plot that we created based on our GPS information. And here, we're good. There's one-to-one alignment. We're not going to have any error. In this next example, though, we have a shift, which is more realistic. So what causes real problems for us is we understand the field here. We have created a bunch of fantastic field data to describe this particular piece of geography, and then we are anticipating and building a model with the assumption that we are summarizing this LiDAR. But if our GPS position is wrong, we're summarizing this LiDAR, which could have either a small impact or a massive impact on our final model development. Of course, the number of plots, the size of the plot, how you locate them are all different things that you can change. I point you towards things like structurally guided sampling to understand how that can work. We're not going to cover that in this series. It's a little bit too far into the weeds. Um, but this concept of why highly accurate GPS is needed is fundamental to understand. If we're in a homogeneous stand in the boreal forest, this might not be a massive impact. There's going to be some error, but if the trees are all kind of the same origin and we're within that same stand type, we're not crossing stand boundaries or something, um, we might be able to get away with it. You imagine now in southern Ontario with a lot of hardwoods, a shift there could actually cause big problems because we might leave trees out that are fundamental. So making sure that you've got accurate positioning is critical. Some field programs go as far as to do stem mapping to try to make sure that they can adjust the field location, or sorry, adjust the GIS plot location so that it absolutely represents where they were in the field before they developed their models. That is very time consuming, but it is critically important to developing these kinds of relationships. So that's another source of error that can potentially impact you. Going back to this though, so we collect our field data, maybe we do some stem mapping, we generate a lot of different metrics that describe the point cloud, and then we go and we build models. You'll often hear random forest is one that's used to do this work. But you could start with, if you wanted to do this on your own, with simple regression. That's not going to be perfect, obviously, but it might give you a good way to understand how do I take, say, one plot metric like diameter at breast height, take the LiDAR metrics that you will see how we generate in future videos in R or in Fusion, and then create a simple regression model to see how do I model diameter at breast height using these. You could use Excel for that work and then apply it outwards. And so you could actually do fairly robust, simple area-based metrics using that without going down the road of random forest just to learn how to do this. And then you can get into more advanced modeling techniques, power functions, lots of different things you can do to start to describe the relationship between these two things so that you can generate a predictor that works all across the forest. And that is really all that's going on in area-based inventory. So I hope that clears it up, and I hope you understand at least some of the levers that you can pull when you're looking at this. And I encourage you to do additional reading in those, especially those materials I identified, to start to understand this. With that, tune in tomorrow for Arc Pro and LiDAR, and thank you very much for listening.